Now let's try r equals to 4 sine 3 theta. So this is very similar to the previous one, except that instead of 2, I have 3 theta. Now, having 3 theta there means that when you increase theta from 0 to 2 pi to do a full turn, then it's going to be plugging in into the sine function. This is the graph of the sine function. The values that gets plugged in would go from 0 to 6 pi, right? So that's why I have the graph of the sine that way. And for 3 theta to hit the first meaningful number in this picture, pi over 2, I like this one because when you have sine pi over 2, the value is the peak values, which is 1, right? So that gives you theta equals to pi over 6. And the next one, when 3 theta is equal to pi, that gives you theta equals to pi over 3. When 3 theta is equal to 3 pi over 2, then if you divide both sides by 3, you get theta equals to pi over 2. So you get these values that I listed here. Because for these values, it's easy to calculate the r value. So for example, when you have 0, you're here, so that the sine value gives you 0, giving you r as 0. When theta is pi over 6, 3 theta becomes pi over 2, and sine pi over 2 is 1. And 1 times 4 is 4. Put this as 4. And if you trust me that these values are exactly the values that give you these important parts, then you can simply think about what happens to this if you multiply these values by 4, this form, right? 0, 4, 0, negative 4, 0, 4, 0, negative 4, and so on. So 0, 4, 0, negative 4, 0, 4, 0, negative 4. Is that right? Pi. Right, so the next one after is 7 pi over 6. And then after this should be 4 pi over 6. Or over 3. Okay. See, 7 over 6 plus another 1/6 gives you 8 over 6. And if you reduce this, you get 4/3. So that's why I'm writing down 4 pi over 3. So if you get go 1/6 of a pi added to this, you get 4 pi over 3, and you'll be back to 0. Okay, let's try to plot these and see what happens, and we'll work with the rest of the table. So, yes.
Are you getting 3 theta equals pi over 2?
What?
Are you getting 3 theta equals pi over 2 and pi?
I'm interested at these values that goes into sine, right?
So you're just choosing these.
Yeah, I'm just choosing. I want to know for what value of theta, the 3 theta is going to give me 3 pi over 2, so that I end up evaluating sine 3 pi over 2, which is negative 1.
Okay.
Which that makes r as negative 4. So you can see that when theta is pi over 2, 3 times pi over 2 is 3 pi over 2, which means you're evaluating the sign at this point, negative 1. Negative 1 times 4 gives you negative 4. Okay, good. So you start from 0, like before. But pi over 6 is 30 degrees. So if you divide this into, this is 30 degrees, that's 60 degrees. It's at 30 degrees that you already hit the peak. So the r value increases until you're at 30 degrees, which gives you the distance of 4 from the origin, and then it turns back. Okay? And then it's at pi over 3. Pi over 3 is 60 degrees, right? Pi is 180. 180 divided by 3 is 60. So it will turn back, hit like that. Hit 0 like that. Right? And then when you're at 90 degrees, 90 degrees is this direction, but look at the value. R is negative 4, right? So you actually as this thing sweeps from 60 degrees to 90 degrees, the actual plot is being plotted behind me, right? And it goes from 0 until -4. That's the peak. It reaches peak at 90 degrees. It just does that, okay? And then another one is this is 120 degrees. 120 degrees is 2 pi over 3. And that's when it comes back to 0. Okay. And the next stop is at 5 pi over 6, which is 150 degrees right here. That's when it hits 4, which is another maximum. I think this should be slightly bigger. It's 4, and comes back to 0 when it's pi. Okay? So you get that. Now here's the next stop. 7 pi over 6 is 210 degrees, which is directly opposite of 30 degrees. But look at this. At 7 pi over 6, you're hitting -4, but 210 degrees with -4 is the same location as, so I'll put, I don't know the correct symbol for it, I'll put 3 equal signs to say, it's not the same point, same value, but on the coordinate it's the same location. So 4, 30 degrees, they point to the same exact location. Do you see it? 210 degrees is this way, 30 degrees is that way. Going 4 steps in 30 degrees direction is the same thing as going backward -4 steps in the 210 degrees, because in this direction, if you go backward by 4, you get to the same point, right? So what's happening from here to there is that it will basically retrace 0 to 30 degrees part of the graph. So you keep following this and you find out that as you go from 0 through 360 degrees, as you go around, this graph is covered twice. Okay? So it's a double drawing of this petal. Okay? So whether you draw this graph from theta going to 0 through 180 degrees, or whether you draw this graph from theta going from 0 through 360 degrees, you get the same picture, because from 180 degrees to 360 degrees, it just retraces the same exact graph. Okay? So the name for this is rose with 3 petals. Now, if you have r equals to 4 cosine 3 theta, well, there's an identity between cosine theta and sine theta, which is that cosine theta is same as sine theta plus pi over 2. Okay? What this is saying is that if you add pi over 2, that's same as sliding the graph left, right? So if you take this graph and slide it pi over 2 left, then you get exactly the cosine graph. Okay? So there's this identity, so that if you have this, using this identity, you can rewrite this as r equals to 4 times cosine 3 theta plus pi over 2, which is, you're just, okay, so you can again write this as 3 times theta plus pi over 6. And what that does is, if you replace theta by theta plus pi over 6, it will rotate 30 degrees. Pi over 6 is 30 degrees. It will rotate 30 degrees backwards. In other words, clockwise. So the graph that you end up seeing is I can't draw this. Okay, so that's the graph that you're going to see. Okay, a 0 and then 120 degrees, and there's another one at 240 degrees. That's the thing that you're going to get. In other words, this graph is exactly the same graph but rotated backwards. And it makes sense because if you plug in 0, you get 4, right? So this graph will start at the peak. In other words, if you have a graph that's given by sine and you replace the sine by cosine, it means it's going to be the same picture that's rotated somehow. That's the general principle. Okay? So, given this, you now have a nice summary of what happens. Here's what happens. Summary. Graph of r equals to a times sine n theta, okay? Or r equals to a times cosine n theta. Okay. It doesn't matter sine or cosine. Has two cases. So case one, if n is even, then you get a rose with 2 times n petals. So you remember the previous example before this, which was that when we drew the graph of r equals to 4 sine 2 theta, when n was 2, we had 4 petals, right? So if I make this into sine of 4 theta, then you're going to get a rose with 8 petals, and so on and so on. Okay? So the number of petals will be doubled if n is even. Okay? However, case 2, when n is odd, then you get rows with just n petals. That's because, as you can see here, when n is odd, when you draw it, it only takes theta from 0 through pi to sweep the entire graph, and pi through 2 pi, you end up covering the same graph, drawing the same graph one more time. So that's what happens. Now that means I find this a little disturbing, but that means you can't draw rows with 6 petals this way, right? Because if you put r equals to sine 6 theta, that's going to give us 12 petals, right? But if I do r equals sine 3 theta, you're only going to get 3 petals. So that means you can't get a 6 petal rose. So what do you do in that case? Well, one possibility is to put an absolute value here so that you don't allow things to go backwards. If you do that, then you're going to get this, and then another one, and then this, and then you get the nice 6 petal thing. Okay? So if you really, really need to draw the graph of r equals to rows with 6 petals, then you need to put exactly this graph, or you need to put an absolute value so that you don't get this backtracking so that you cover the same graph twice.